So we've seen some great things that you can do with vector spaces, wonderful conveniences. You only have to prove a theorem one time, and then every vector space that you should happen to find in the future, that theorem will automatically apply. The cost of that is you do have to actually confirm that the object you're looking at actually is a vector space, and this is not a formality. This is something that is a legitimate worry. Not everything is a vector space. And here's an easy example. This is a plane in R3. Y'all will recognize that this is the equation of a plane. So this is a particular plane in R3. And if I were to say, yeah, let's just use the usual addition and the usual scalar vector multiplication and call this a vector space, it's not. It's not a vector space. In fact, the usual vector addition isn't even an operation on this set. So, in particular, notice if you take this point that satisfies that equation, and you take this that satisfies that equation, when you add them, the sum is this, which doesn't even satisfy that equation. So you can't call this an operation of addition on W, because two vectors in W add by this operation to give you something that's not even in W. So this is not an operation at all. And so you certainly cannot think of this as a vector space with those operations. Okay, so you have to be careful with that. There's another thing you have to be careful of, and that is keep in mind that when you define a vector space, you're obligated to supply a set, some sort of vector addition, and some sort of scalar vector multiplication. Okay. But you're not obligated to choose the operation that someone might expect. Right now, this again is a wonderful flexibility. It gives you the power to define lots of different vector spaces. And there are some natural vector spaces where these operations are perhaps not what one would expect. As a result, you've got to be very careful when you're doing vector space algebra. Don't just assume that the operations are what you would expect. Be very clear and precise about what your operations are, and be very careful to stick to those rules as you do algebra in that vector space. So here's an example. You'll recognize this is the same plane we were talking about a minute ago. I've not called it W, I've called it something else. I've called it V. And with what I'm going to do with this plane, same plane, is I'm going to define new operations. I'm going to define a new addition by this formula. Now, that's not the expected formula. This is not how we have added vectors in the past. Importantly, in the past, when you've added vectors, you have added vectors in the vector space R3 that had a different formula. Here we're just defining now a different formula for addition. Okay. Likewise, there is a scalar vector multiplication that I'm defining here. And again, this is not what you would sort of expect. There are these sort of extra terms here that seem out of place. Okay. That being the case, this set with this new weird addition operation and this new weird scalar vector multiplication, this is a vector space. This satisfies all of the rules listed. It's a strange vector space, but nevertheless, it is a vector space. I encourage everyone to go through and confirm that these do satisfy all of the rules. Some hints that you might find helpful when you're going through the rules. This is the vector that is the additive identity. This is the, what you might call the zero vector. And again, now the students will object and say, no, it's not. Look at that. There's a 1 in there. That's not a 0. Don't forget, what we call the zero vector is the vector that behaves algebraically with our vector addition in this specific way of being an additive identity. We're not making a cosmetic observation about everything has zeros in it. Right? So confirm for yourself, but sure enough, this vector, when you put it there, add it to anything you like, and you get the exact same thing back. So that is the 0 vector. Similarly, this is the additive inverse. This is what you can add to any vector and get the 0 vector. Careful. That 0 vector. Okay. So it'd be a good exercise for everyone to go through, show that these two operations satisfy the 8 required properties, with these being the special vectors included. Okay. A few other facts to mention. These are true facts about vector spaces. These are not properties that you have to check. These are properties that can all be proved from the 8 given requirements without making any additional assumptions. So you get to use these facts for free anytime you're talking about a vector space. In particular, there can be only one 0 vector. If there's an additive identity, there's only one additive identity. And think about how you might prove that. Likewise, the negative, the additive inverse, is also unique. The number 0, the scalar real number 0, if you multiply by any vector, you get the additive identity vector. Now, again, in Rn, this is obvious. But this is a statement that's being made about vector spaces in general. Okay, so it's not immediately obvious that this is true, but you can use the 8 properties defining a vector space to draw this conclusion as an abstraction. And likewise, any real scalar times the 0 vector gives you the 0 vector, and the scalar -1 times any vector gives you the additive inverse of that vector. So all of these are familiar looking things, but they are not obvious. The good news is they are true.